Okay, so now let's continue our discussion on how we're going to use energy and power flow in practical system modeling. First, consider the types of variables that need to be used. We know that we can quantify energy by the product of two variables. So, for example, in mechanics, we can calculate the change in energy or the work done as the force times some change in displacement. Say, like if you had a spring and you compress that spring, you could calculate the change in energy stored by this pair of what we'll call conjugate energy variables. As another example, in a hydrostatic fluid or hydraulic fluid example, you might have a pressure times a change in volume. So these are, again, as I said, we're going to call energy conjugate variables. And if you look up the word conjugate, it means taken as a pair. Together they give energy. And usually these two variables are chosen as what are called extensive and intensive variables. And you might recall these definitions. Extensive variables are those that have a magnitude that depends on the amount of the system that enters into the calculation, or in this case, the energy transaction. So an extensive variable type might be a displacement or an angular displacement for mechanical systems, or in electrical systems, a charge, maybe entropy, mass, or volume. As you can see, those sort of sum up to give you a certain variable. So it depends on the amount. Whereas an intensive variable are those that depend on only a function of the field in which the system resides, so like forces and torques, voltages, and so on. So in this case, for example, pressures and forces are going to be intensive variables, and the volume and displacement are extensive variables. Now, when thinking about power flow, and we were looking at these system representations with power flowing through some area, we're going to define at a system boundary, and here's a boundary as shown, power flow from or to the environment as being sort of conceptualized as occurring through these power ports. Okay, so here I'm kind of sketched out a power port, and there's power flowing, and I'm showing it flowing from the environment into the system. Sometimes we assign that as a positive change in the power flow, meaning that it changes the energy in a positive way in the system. So we usually use that as a positive power convention. We're going to start drawing these kinds of representations using words or symbols to represent systems. And graphically, we're going to represent a power interaction between, say, system 1 and system 2 using just a single line. And we're going to refer to this. We're going to refer to this as a power bond, right? The power bond is just a solid line. And when you have a positive direction, and so this is showing no sign definition, but we could have a preferred sign convention, and if we do have that defined, we use in a bond graph notation, we use a half arrow, as you can see here. Remember, we've already talked about signals as having just a full arrowhead, so we don't want to confuse signal flow, with power flow. So power flow is a convention that was adopted by Professor Paynter back in the late 50s, and a half arrow is specific to designating power flow. And in this case, the power flow is positive from system 1 to system 2. Just like we quantify energy with conjugate variables, we have also power conjugate variables that we select, and their product gives us instantaneous power on, say, one of these power bonds or at a power port. And you should be familiar with the fact that we always kind of try to factor power into two components, such as force and velocity, voltage and current. And sometimes we talk about shaft power, for example. When we talk about shaft power, the way we quantify that is with torque and shaft angular velocity, right? So those types of variables are going to be generally defined as effort and flow variables. And effort and flow variables give you, through their product, power. Remember, this is always in units of watts. And on our graphical representation, as we drew before, here we have positive power from system 1 to system 2, shown with power bond, and we'll label a power bond when we need to show that we've got an effort and a flow, and their product gives the power that's being transmitted across that connection or through that power bond. And I'm showing here now a table summarizing the power conjugate variables in all the various energy domains that we might be interested in. Again, the general notation is an effort variable is E, and the flow variable is a little f. But in all the different energy domains that we might think about, we have effort variables and we have flow variables. As you can see, for example, electrical is voltage times current, and all of these in this column just show the power product. And we're going to show that all of the methods that we'll talk about with regard to using a bond graph approach can adopt these types of power conjugate variables, and then we sort of have a unified way of looking at these systems. Okay, and by always tracking power with these variable pairs, it also is convenient to express relationships for the physical laws. We'll see that later. And also, in some cases, it can help certain analogies. There's a lot of different analogies that we can use between systems, and there's a analogy between the different various systems that we can use that are sometimes helpful. Now, as I've discussed before, it's helpful to start looking at a system and thinking about where is power stored and where is it dissipated. I kind of have drawn a little system diagram here, and the blue might represent system elements. Maybe those are storage, and the red ones maybe dissipation. So sometimes when we start subdividing a system to model it, we then start thinking about interactions between them, and I'm showing here these bilateral arrows, meaning that we've got conjugate variables, right, exchanging power between these various system components, right? Now, the bilateral signals are needed because, right, that represents the two power conjugate variables that we've been thinking about. Sometimes we show these two arrows, but really most of the time it's most convenient just to show power interactions with a single bond. It's much more efficient. We'll discuss certain concepts shortly with regard to causality with the bilateral signals, and that's helpful. To illustrate how we can use these power flow concepts, I've sketched out a little example here. This is a shipboard propeller drive. There's two power sources, say two engines driving through a reduction gear, and then there's a drive propeller shaft. There's some bearings along here. And let's say you were just starting to model the system. What we want to do is we want to identify some key components and possibly some system elements that might be of interest. And so what I've done down here at the bottom is drawn what we call a word bond graph. So here, the early stages, we haven't really started analyzing these in detail. Let's say we want to break up the system to be studied by various people. And you might say, oh, I have a power source here, and then I have power flowing. And this whole element here has power flowing from the two power sources. That's a word, right? And there's actually power flowing in all of these elements here into a thermal domain. I haven't, again, given any detail to this, but there's bearings, there's energy stored in the shaft. Let's say that shaft is compliant, right? So it's being twisted, so there's energy being stored in there. There could also be energy stored in that shaft in the fact that it's rotating, so it's got kinetic energy as well as potential energy. So there's a lot of detail that's left out, but sometimes a word bond graph like this helps you begin trying to analyze the system. The propellers here, and then see there's a transmission from the rotational power of the propeller to basically the power of the vehicle in its motion. Okay. We sometimes talk about power-based multiports, and this is one of the useful notations that we pick up in using this bond graph approach, is that we can identify system elements, and we have not detailed this very in great detail yet, but we can see that we've got multiple ports coming into a system. So this is sometimes what we might call a multiport. There's no detail here, right? So this is just the concept at a very abstract level. We still need to kind of dive inside there to figure out what's in there, and that's the kind of modeling that we'll do in this course, is studying the actual system and figuring out how do we break this up and detail it out so that we can study it and quantify its behavior. So, while schematics and these kinds of word bond graphs are useful, we still, and they can help us guide us, make decisions on how we want to model the system. That's a lot of assumptions need to be made on how detailed you want to be. We still at some point need to adopt some physical laws, and in that way we need to define multiports in more detail than this, although again this can be helpful just in getting yourself started, figuring out what kind of system elements you have and so on. One other concept I wanted to introduce here early on is as I mentioned, the concept of causality. We've already shown that we can show that this power interaction can also be drawn with bilateral signals. So what these two signals represent are the two power conjugate variables. So one of them could be an effort, one a flow. And so note when you have signal flowing from S1 to S2, that means that system 1 is specifying that variable to system 2. We don't yet know which variable this is, and that's one of the things that we need to denote on this graph. So we know that at every power port, so here I've drawn sort of a little power port, and there's always going to be one variable, either effort or flow, that's an input to that power port, and then there's always going to be an output by the nature of physical dynamics. So this, again, product is always going to be power. So the way we're going to denote that, these methods will become more formal later, but just to show you the notation, if we have system 1 and system 2 connected by a power bond, we can specify that system 1 imparts an effort by using what's called the causal stroke, and this is just again a vertical line here. So when we draw the causal stroke from S1 to S2, so the stroke is next to the S2 here, basically what we're saying is that S1 is imparting effort to system 2, and system 2 in return specifies flow back to system 1. And alternatively, you can see, okay, S1 could specify flow to S2, and S2 could specify effort back. And the way we would specify that is by moving the causal stroke next to the S1 here, right? Sometimes we think of this as kind of pushing, kind of like a force, so that's an effort. And here this looks like more like it's pointing, and that's sort of more as a flow being specified. There's different ways that you can try to remember these notations. Again, right now we're sort of arbitrarily assigning these causalities. Later these will become, there's a more formal method for assigning causality on an entire bond graph, and that's a very important part of the modeling process. Again, later, as I said, we'll introduce very specific ways of assigning causality to a complete bond graph and to all the power bonds. And causality is important. It tells us a lot about how power conjugate variables are related on every bond, and this turns out to be very useful information. Again, in early stage models, it's difficult to know what the causality is going to look like, but if you have specific systems that are like sources, like let's say you had a battery, you know you might assume that battery is specifying an effort to a system. So there's a system connected to this battery. It's easy to say, oh, that battery specifies an effort to whatever is connected to it. Again, we're going to find that causality is very helpful for deriving system equations. We spend a lot of time using causality in this way. And it tells you something about whether the equations that you derive are solvable. In addition, causality has some physical meaning. Remember that example of having just forces on a mass. Imagine that you were trying to impart both. In other words, let's say you had this mass and you said, oh, I'm going to put both a force and I'm going to also specify the velocity. So you have some system, right? And you have the mass over here. And what you're saying is this system, whatever's attached, that's going to specify both effort and flow, okay? Is it possible to do that? And if you think about it a little bit, Newton's law will prohibit that. I want to let you think about that a little bit. Newton's law, remember, says that the rate of change of the momentum is the sum of the forces. So if you think about it, if I put force on a system, that will automatically determine what, not only what the acceleration is, obviously, but by integrating this, you determine the velocity. So you can't arbitrarily come in and specify both force and velocity and have your model make any sense, right? So there's some physical meaning when we say that we can't specify both effort and flow. And so causality gives us some insight into some of these physical limitations on our models. Lastly, I want to emphasize that when you assign positive power on a bond, right, that's independent of causality. So causality has nothing to do with that. You could assign causality on a bond without any power, or you could have causality and sign both. So you could have causality being specified, so that flow is being specified in this direction, and then power is also being specified in this direction. But on this power bond, effort's being specified right in this direction, but you could also have power being specified. So the two assignments of causality and power are completely independent of one another, and it'll depend on the rest of the model as to how it's used. Here's a couple of different examples. Let's say you had a fixed wall, right? So that's got a known velocity, right? Because it's not moving, and then you have a spring. How would you assign causality there? Think about that for a second, right? The wall is going to tell that spring that it has a known velocity. So how does it convey velocity information? Well, causally, it does that by putting a causal stroke here, right? It says, oh, my velocity is known, it's 0, right? How about a battery against a resistor? Kind of already mentioned this one. If I specify the voltage, then it's specifying effort into the resistor. If I have a specific type of pump that I know specifies pressure, obviously that has to be specifying effort or the pressure, right, into some pipe element. Let's say I have the mass and I have a model element that represents its weight, right? So like this is mg, say, and this is the mass. So this is specifying the gravitational force on the mass. So it's a weight, right? If you want to draw weight here, or force, that's causally also specifying mass. So you can see the couple of different examples of causal assignment here. Think about these on your own and review what I've just talked about here and see if you have a good understanding of how we assign causality, at least when we have a good idea of what one element in a pair might do. Again, when we have large systems with multiple power bonds, we have specific ways that we assign causality on all the elements. Finally, I just put a diagram here. As I've mentioned, Professor Henry Paynter developed bond graphs starting back in the early 50s and 60s, and followed on by many of his students and others that have contributed to bond graphs. But in a paper that he published back in the 80s, he gave this diagram showing how early on he had been thinking about this concept of bilateral signals as conveying power and also sign. And he pointed out how, he had been working on these hydraulic power transmission systems. So he was interested in modeling these systems, and this is a lot of what motivated him to develop the bond graph method. But this is interesting because you can see in conveying hydraulic power from the reservoir, right, into this conduit, he shows a flow variable, and this is head, so this is a pressure variable, right? But that's head. But that's a power product, right? But you can see, at that time he had not thought about the fact that you can't specify both. If you were drawing this, if you had to draw a reservoir and conduit, how would you label causality on that? Pause and think about that. Okay, so you know that the reservoir is something that we model as, say, here it is. It's not going to change height very much. So that's going to have a specified pressure, right? Because we're going to say that the height of that water is not going to change very much. But when it's known, it's not changing very fast. So it's always going to have the same pressure here. That means that causally. So really, the way this should have been specified, if it was redrawn, was that pressure is specified into the conduit, and the conduit specifies flow, right? So this is really the way it should have been drawn with bilateral signals at this point. So there's some neat historical significance to this diagram. Another thing to think about with regard to this is note how he's got multiports here that are needed. He's got this penstock here, and it's got multiple, right, ports, right, because he's got the surge tank coming into it, the conduits coming into it. So he's basically representing, right, an element that has 3 different ports, and that's one of the nice properties that using multi-port expressions allows you to interconnect systems this way.